Have you ever been sitting at home during a thunderstorm and the lights flicker for just a second but stay on? And other times, that same split-second flicker is followed by a total neighborhood blackout. The difference between those two outcomes comes down to a massive, invisible battle happening miles away. The power grid is a delicate ecosystem. We normally think about keeping it balanced in terms of basic voltage and frequency, but there is a very specific hidden challenge that engineers call transient stability. To put it simply, transient stability is about survival. It is the ability to keep gigantic, physically connected machines running in perfect rhythm across hundreds of miles, even when a sudden, violent shock threatens to tear them apart. Consider the sheer physical scale of the machines powering the grid. Inside these heavy industrial housings are solid steel rotors weighing millions of pounds, spinning at exactly 3,600 revolutions per minute. Because they are all electrically connected to the same grid, these massive spinning rotors have to turn together in perfect unison. Think of them as a convoy of heavy trucks roaring down a highway at the exact same speed, tied together by invisible rubber bands. If one of those trucks hits a massive pothole and suddenly slows down, the rubber bands stretch and snap. In a power plant, if one generator hits a bump on the grid and loses its rhythm, the physical forces at play can destroy the machine and pull the rest of the connected convoy down with it. Let's look inside one of these generators. There are two fundamental forces constantly pushing against each other. First, you have the mechanical force from the turbine pushing the rotor forward. Against that, you have the electrical force from the grid itself, pushing back like a heavy headwind. Under normal conditions, these two pushes are exactly equal. It is a perfect tied tug-of-war, keeping the rotor spinning smoothly at a constant speed. But imagine a lightning strike causes a short-circuit fault on the transmission lines. In an instant, that electrical resistance pushing back completely vanishes. Yet the steam or water driving the turbine continues pushing forward with millions of pounds of force. With nothing pushing back, the machine surges forward. The rotor starts accelerating rapidly, absorbing all that unchecked mechanical force as raw kinetic energy. This massive buildup of speed has to be countered quickly to avoid a crash. Engineers need a way to measure whether a generator can survive this sudden kinetic energy surge. They use a visual scorecard called the equal area criterion. This graph plots power transfer against the angle spread of the rotor. Because the machine is spinning so fast, this angle is basically its timing. It shows exactly where the rotor is positioned relative to the rest of the grid. The horizontal dashed line is our steady starting point, where the forces are perfectly balanced. When the fault hits and the machine speeds up, we track that buildup of kinetic energy. We call this shaded region, Area 1, the acceleration period. You can think of it as a growing energy debt. Once the fault clears and the grid reconnects, the electrical resistance slams back into place. The machine begins to slow down. This brings us to Area 2, the deceleration period, where the grid burns off the energy debt as the operating point rises to its peak. Here is the core mathematical rule of survival. To keep the machine from breaking apart, the grid's ability to decelerate the rotor, Area 2, must be physically large enough to completely cancel out the energy debt taken on in Area 1. This chart shows what happens if the fault lasts too long. The initial energy debt becomes too massive. The machine slips completely out of sync, and instead of sending power out, it suddenly starts sucking power back from the grid, pulling the whole system down into a runaway failure. This simple visual comparison of areas tells us whether a multi-million-pound machine will safely rock back into rhythm or tear itself apart and trigger a regional blackout. In this battle of forces, time is the ultimate adversary. The immense physical inertia of these spinning machines means that once they start speeding up, the laws of physics are working against the grid. Every single millisecond that a short-circuit fault remains on the line, that acceleration area grows larger, and the generator's kinetic energy debt climbs higher. This graph tracks the position of the rotor over time. There is a precise, calculated threshold known as the critical clearing time. If the fault isn't cleared before this exact fraction of a second, the energy debt becomes impossible to absorb, which is why line 4 shoots infinitely upward into complete instability. Because this point of no return is reached in less time than it takes to blink, we can't rely on human reflexes to fix the problem. The grid defends itself automatically. The primary defense comes from high-speed circuit breakers. Their job is to violently sever the faulted power line from the rest of the system before we ever reach that critical clearing time. The moment the fault is cut off, automated systems like electronic stabilizers immediately kick in across the network. They adjust the electrical resistance on the fly, acting like massive shock absorbers to help the remaining generators settle back into their steady rhythm. If the shock is too great, the system turns to a final failsafe called load shedding. By intentionally dropping power to specific, non-critical neighborhoods, the grid sheds weight to save the entire interconnected convoy from a total collapse. That split-second flicker during a storm is the visible sign of a million-pound tug-of-war, won by grid engineering.